All right, and let's get into basically question 4. So let's design some new pipes. Our last problem for this practice exam. So trying to design a new material for water pipes. Worried about repeating the Grace Fiasco. My pipes have a diameter of 35C. Thickness of this, I need to go immediately into, I'm going to actually go ahead and clear. So this is important. So I'm going to actually quit the whole kernel. I would suggest like sending in multiple notebooks in your submission and make sure you clear everything because you don't want any crosstalk. So, but that's just my opinion. So I'm told that my diameter is 35 centimeters. So radius equals 35 divided by 2 times 10 to the minus 2. And then my thickness is equal to 0.5 times 10 to the minus 3. So let's do R over T. And what do you know? That's a very, very thin wall pressure vessel. The pressure exerted on the walls of the pipes to be approximately 26 MPa. I've developed a new material that when stressed with these conditions, so that's what San Joaquin County claims. So they claim that delta P is this, but developed a new material when stressed under these conditions will exhibit a strain in the 2 direction of 0.01 and the 1 direction of 0.08. So basically, I know it's a thin walled pressure vessel. So I could start to write out that my stress tensor is equal to, in my 1 direction, that's my hoop, longitudinal, 1, 2, 1, 2, 1, 2, 3. My strain tensor is just going to be EH, EL, 1, 2, 3, 1, 2, 3. And so I know that my sigma H is equal to delta PR over T. My sigma L is equal to sigma H divided by 2. And then I know that my epsilon sub H, my epsilon sub H is equal to 1 over Y times my sigma H minus nu sigma L and my E, essentially. My sigma L is equal to 1 over E times sigma L minus nu sigma H. So I can go ahead and I can start setting up those equations. So I know that my sig H equals del P times R divided by T. Sig L equals sig H divided by 2. EH equals, and this is why it's kind of really unique to write it in Mathematica, because you kind of start to see what your equations are looking like. EL, and then that's equal to 1 over Y times sig L minus nu times sig H. So I can start to see the only thing I need, I have basically several unknowns here. So I have my del P, my nu, and my Y. I'm also told the values of basically 0.01, 0.08. So I can set those two and solve for 2 unknowns. And again, we're assuming that delta P is going to be 26 MPa. So let's go ahead and let's kind of put that in there. Del P equals 26 times 10 to the 6 MPa. So the pressure exerted on the walls of the pipes. So got this. Still have 2 equations, still have 2 unknowns, but we could solve for that. So EH, set that equal to, so in the 1 direction, it is 0.08. And then EL, set it equal to 0.00, basically 0.01. And let's do solve for, excuse me. Let's do numerically solve. Oops. Ooh, interesting. Doesn't like that one. How about let's do numerically solve? Do n solve. Sometimes you just want to check on what Mathematica is thinking. Ooh, interesting. Why don't you like that? Yeah, sometimes Mathematica just really doesn't like. And. Yeah, let's just do solve. There we go. The answer is obtained, blah, blah, blah. Verify the result. So, anyways, we could get those values, and we find the following. So, this, and then let's put this here. Y equals this. Let's hide those outputs. So I could look at my EH, EL, and then get all those values. Fantastic. So found the Young's modulus, found the Poisson's ratio. what is right at the full stress and strain tensor? We have those values. What's the maximum of, what's the maximum value of shear stress? So that's just going to be basically my sig h divided by 2. Because again, if I know that my sigma 1, my principal stress rate, sigma 1 is equal to sigma h, sigma 2 is equal to sigma l, and sigma 3 is equal to 0. So if I write the full 3D Mohr circle, we've got that. What's rotation to principal stress? 0. Maximum shear, 45. Explain the fracture in the diagram, what is happening here. So this fracture is not normal. We should be fracturing like this, so there must be some type of like impurity or something else strange going on here. It is not normal. When a material fractures, there are 2 energy contributions that determine what will be the critical, so again, when we're doing that free energy contribution, we have basically relieving our elastic strain energy. And then also basically, again, surface area accretion. So elastic strain, that wants us to propagate and crack. Creating surfaces do not want us to crack. Material fractures, yeah, so those are for this problem. What is the critical crack size? So my material, to me it behaves a lot like, this is like 91, so it's a pretty strong polymer, but this should be like a polymer biomaterial. It's definitely not a ceramic. So I'm not going to use my Griffith criteria for very, very brittle materials. So remember, stress at failure equals square root of 2 gamma E over pi A crit. So I'm going to use instead our OR1 theory for ductile failure, which is going to be sigma F equals square root EG over pi A, where sigma failure, I'm going to set that equal to sigma hoop, and I can then solve for the rest of those values, to figure out what is the basically the critical crack size. So I'm given that energy release rate value, so I'm just going to go ahead and solve that sig h set equal to square root of my y times my g, which is going to be 7,500. Luckily, I'm already in my units that cancel out, divided by my pi times my a. And then do this, close that, solve this, and that's pretty big crack size. 2 micrometers. It's decent size. So that's it. That's your whole exam. So study hard, and I look forward to seeing everyone at the review session, and I'll see you all later. Thanks. Bye.